So particle physics is the area that studies the element component of the universe, not the matter of the universe itself. We can study particle physics in two ways. In nature, so studying cosmic rays, or we need to build an accelerator to generate our particles to be studied. So basically this machine were what was providing the protons for the discovery of the Higgs boson.
Yes.
Nice to meet you.
We already follow a course of yours at CBPF.
First of all, thank you very much for agreeing to this. This is really great.
So which level of details we should...
Whatever you feel more comfortable with. So they have seen the Science Gateway, we were at the CMS control room. They have a rough idea of how to produce a proton beam. I tried to explain that to them, but everything in between, what happens, producing protons and having them in the LHC, I didn't tell them about. I told them there are several steps. It's like driving a car. You accelerate with the first gear and then switch higher, accelerate. But I didn't tell them about the booster or anything like that.
Okay. So to complement this, so we will see the Linux, so how actually the source of the protons.
Oh, we come to the bottle as well?
Yes.
Oh, perfect. We were just talking about the bottle. I told them, yeah, that's great. This is awesome.
And I will talk about some technology for acceleration and then see some accelerators.
Yeah.
Have you been here before?
We have been here, but I didn't explain anything because I didn't know what to say.
Okay. This is a beam test facility for testing things. So this is a very small accelerator. Then there we have Lear accelerators that we will see better later. Behind that wall we have LINAC 3 where we actually start, it's a linear accelerator to start ions acceleration. And then behind that, the other wall, it's PS actually. So we have PS right over there. This is not glamorous, but for me this is the most pedagogic thing that we have here at CERN to explain accelerators. Okay, so what we have here, it's a piece of an accelerator of LINAC 1. This was in function started in '59. So it's pretty old, but it doesn't have any glamorous place for it, but for me it's really nice. Here the source of the proton was slightly different from nowadays. We used what we call the static accelerator, so we have a very high differential potential, 750,000 volts. We call this accelerator Cockcroft-Walton accelerator. The problem is that with the Cockcroft-Walton is a static differential potential, so we cannot accelerate further, otherwise you need even a higher differential potential. So the solution for that was what we called drift tubes. So we have a differential potential, so positive, negative. If this is static, it will create this electric field. Electric field is the only way to accelerate charged particles, electric fields. And it will create this electric field and will receive this kick, this acceleration. What is the problem? When it's static, that's it. You gain the energy, but you cannot continue accelerating. The magic here is that the particle will pass through this conductor, and every time that they are inside this conductor, they don't see any electric field. But when they go from one tube and the other, they feel this differential potential. They will see an electric field. Okay, so for example, this proton is passing here. It will see an electric field, a differential of potential, and when it's in here, we have a mechanism to change the polarity of these conductors, and again we will see the same electric field as before, and is able to continue accelerating. So the magic here is that we have what we call an RF voltage. So this means that there is a frequency in this voltage that is synchronized with the particle, and as this frequency, this period is the same, and the particle is getting velocities, meaning that to continue to be synchronized, this tube length must grow with the acceleration, but also the gaps. So an exercise that I like to show to the people when I bring here is to go look inside the drift tube linac and see that it's growing, so there is smaller and gets bigger and bigger tubes. First thing that we need is actually how to generate the differential of potential, the electric field, to accelerate the particle. The idea here is that we could build one of these very long, a linear accelerator. However, it's cheaper if we make it circular. There are some advantages because the size is limited, so it's cheaper to build it. And also, if it's a collider like the LHC, we can reuse the protons. If the particles don't collide, we can reuse them in another CERN to collide. Yeah. So there is some advantages to have a circular collider than a linear. The linear, there is another advantage that it's pretty simpler to design. I mean, the studies behind the linear accelerator, it's simpler because of the stability of a circular collider. You're expecting to have an operation of hours. LHC has a record of 2 days. And just to have a notion, in 1 second, it does 11,000 turns. And in every turn, if you have an instability, you can lose the beam. So it must be very perfect to allow the protons to circulate for billions of turns, right? So if you wanted a linear, you just need to create this electric field with this mechanism. But if you want a circular, we need other elements. The first one we called dipole magnets. If you have a magnet field and the particle is moving, it will generate a force perpendicular to these vectors. So it's dipole because it has 2 poles, north-south, and it will generate this force to bend the particle. So, and if you, of course, if you have a collider, you in the other direction, the magnetic field will be opposite in order to bend in the other direction, and then you make them to collide. Okay, this is the dipole, and then because the particles are not accelerated one by one, but it's they have a distribution in space, but also in momenta, so in energy, because they don't arrive in the accelerator at the same time. So they have slightly different energy between each other. What will happen is when they go to the dipole, they will have slightly different deviation. They will do the curve slightly different from each other, and this effect we call dispersion. In a tiny accelerator, you can make particles to survive few turns. In a large accelerator, you will immediately lose the beam. So in order to solve it, you need this third element we call quadrupole. So instead of having only 2 poles, we have 4 poles. and it has now the force is we call focus in one direction, but because of the Maxwell equation we can only focus in a direction and not in the other. So in the other will defocus. It will open the part. And then of course to compensate this effect you need another quadrupole to focus in the other direction, and it will open into the other, so it will defocus in the other. But if you put these elements around your circular accelerator, we call that now the particle will have a Betatron movement, so it will go up and down, or a wider and narrow, and the beam is stable now. So now I would like to show you the linear that we use it here, that were in function until 2000, at the end of 2018. Okay, so here we have something nice to show before I show the linear itself. It's we call RFQ. You can point, you see that there is some undulations. So it will provide the electric field to accelerate the particle, but it has a component of quadrupolar. So once again, to focus the beam, make it stable just after extracting from the source.
Who built these machines or this accelerators? This is all built at CERN, or it's not that you go to the supermarket and say, okay, give me an accelerator of this size, and somebody has to build these kind of things?
So the design is from CERN. The manufacturer is, you create an order, okay, we want that, that, and you ask for industry to build it. Here we have a tiny one, LINAC as well. Also this is from LINAC 1, and here the particle were even in lower velocity because you can see the gap between the tubes is very small. So when the particle gets faster, the gap and the tube get larger. But this is just for LINACs. When we go for higher velocities, we need a different technology. This is only works for, I'll say, low speed. It's the one that we saw, 0.3, 30% of the speed of light. Then the new one that we use actually can go up to 0.4, 40% of the speed of light. Why? It's just because if you wanted to get to high energy, you have to change the frequency or make it longer. But if you go for higher frequencies, the energy is, I mean, it became like a radio, an antenna, you know, it's emit the electric field to the media instead of accelerating the particle. So this is LINAC 2. It was in operation from the 80s until 2018. So basically this machine were what was providing the protons for the discovery of the Higgs boson during run 1, so 2010, 2012 period. So we have the drift tube, and now we actually can see, we could not see before in the piece of LINAC 1 outside, how it's fed the conductor is with our RF generator, which will provide differential of potential. So this is the RFQ, is the one that provide the electric field, so accelerate, but also has the focusing element that I just showed before entering this room. And then, even very interesting, inside this box, we have the the source of our protons. It's a duoplasmatron. Here we have a maquette. Inside we have, it's not small like this, it's a really huge bottle of hydrogen, and hydrogen is the source of our proton. The gas will go inside this chamber, and then we'll have a ionization with the pressure and also with the very high differential of potential, so it will make the proton accelerate and shield the electrons to remain there. So basically extracting the electrons from the atom of hydrogen. Any question?
How long does this bottle last?
This is a great question. This is actually it's a question that I ask to my students. Yes. So we can spend 10 to 16 protons. So 10 to 16 is the order. 16 is the order. And then my question generally is how long it lasts, and this is basically Avogadro number, which is 23. So 10 to 23 is the order of the Avogadro number, means that it's kind of infinite, but actually we change it every year. This is the control room of this complex that was used in the past. Now this is not used anymore here, everything is CCC.
It's almost sad.
It's very sad because if you look to the pictures, it was very glamorous, it would look at very, but nowadays they have to replace with the modern screens,
Sure.
Well, kind of modern screen, but in the past it was top technology.
Very retro style.
Yeah. Now I will, as we talk about the facility, I can explain a bit where we are. So this is schematic of the accelerator facility here at CERN. We are next to LINAC 3. LINAC 3 is just the next wall, and before LINAC 2, so this machine until 2018, was the one providing the proton that go to the booster. So here, as I said, the speed is 30%. Here already is 90% of the speed of light. And then we go for PS, which is the oldest synchrotron. So this technology of having dipole, quadrupole, and RF cavities accelerators is the oldest of CERN. It's from 59. It's not the first accelerator, but it's the first synchrotron. The first accelerator is the SE, we will see later. And this just 600 meters and already got to 99% of the speed of light. And then we go to SPS, that is already 7-kilometer machine. We go to 99.999, the speed of light. And then at the end we go to LHC, the dark blue one, and then the protons get to the speed of 99.69. I will not say 99. It doesn't sound a lot, from 99.99 to 99.999999, but if you take this in energy, that is a big gap, because this in energy, it's 450 giga-electron-volts is the unit that we use for measuring the energy. So 0.45, if you, so 0. Something, and here get to 6.8 tera-electron-volts. And why we want more energetic is because Einstein, if you have higher energy, you have also higher probability to produce new particles with higher masses. So it's interesting to have higher energetic beams.
The four experiments are distributed along this circle. Why are they at these specific points?
Okay, that is a very good question. This is not really the right position, okay? So Atlas is here, LHC and LHCb are closer. So we call this interaction point 1. There are 8 interaction points. So this is I1, I2, I3, and then in the exactly the opposite side of the ring we have CMS. The reason to have this position is to have some kind of symmetries that is really helpful to maintain the beam stable. If you put in a symmetric position and in the collision point actually you exchange from, so this is clockwise and this is anti-clockwise, you change the position, and if it's asymmetric, meaning that you have troubling calculations to solve that system, and this is simpler to solve it.
So we know that the LHC is 100 meters below ground. How deep is the SPS?
SPS is not much.
So you still need like a transport system down, right?
Yes. Yes, yes. It's not much. And then nowadays I'm working with the FCC project.
Ah, FCC, okay. That's the 100 kilometer
Future collider.
the future collider.
It
Yeah.
means future, okay.
Yeah, future circular collider, and that will be 91 to 93 kilometers, and that will be 200 meters underground. So you need to bring the protons 200 meters for the injector will not be LHC, but will be SPS. Yeah. A lot of people think that it's LHC. No. It's directly from SPS. SPS will be updated. The limit of energy of an accelerator, of a circular accelerator, are the dipoles, because the dipole has a magnetic field to bend the particle, and if it's not too strong, you're not able to cure the particle if they are faster. So if it's stronger, you can go to higher speed. That is the limitation. Now we are going to see the circular accelerator, a storage ring. This is not for protons, it's for ions. Not so glamorous, it's a bit dirty, a bit dusty. Also we have birds here, you can see. But yeah, this is a storage ring. We can already identify some elements. So as I say, the dipole is the responsible to make the curvature of the particle. So is here in orange. And the quadrupole in this accelerator are in blue. Very important element is what generates the electric field to accelerate. Here we have a cavity, so an RF cavity, are the two boxes over there. That is the accelerator itself. This one is actually very funny because when it's on, you can hear it. There is some magnets there, the green ones at the end, which are the extractor and injector of these, and when they feed with the magnetic field, actually has a sound. So it's funny, like trak, trak. Yeah, you can hear it. It's very funny. But ions runs we have only at the end of the ear, so it's off. The pre-injector of this accelerator is LINAC 3 that is behind this wall, and they are working on it. They are working on the electronics. What we have here, so this is the kicker. This part here is to make the particle a bit side of the orbit, so in order to actually get out to the ejector. So actually it's a very funny what they do. So the LINAC 3 goes in that direction, then it does a curve almost 180 degrees, comes here, and then to the ejector, it circulates to the PS, which is the accelerator that I told before, that the oldest one from '59. So we have the kicker, and we have something very interesting that is not common in many accelerators. We call these electron cooler, these two towers here. And this, we say it's an element to change the charge density of the bunch of the beam. Why we need that is that is required for operation in the next accelerator to have a different charge density. So this means the volume of protons or ions in this case that occupy in space, you want it to be smaller. And this is actually one of the few ways to do that. I will go a step back just to be clear. If this system is conservative, so I turn off the RF cavity, so no electric field, and this is a vacuum, the particle will keep circulating. It's a conservative system. So what happens in the quadruples, they will just change the shape, but will not change the volume itself. But if I want to change the volume, then I need to kind of not be conservative. So what we do here, we have a tower that will send electrons, and the other will collect the electrons. It's we call the stochastic effect. Have a Colombian interaction with the ions or protons with the electrons in order to change the charge density of your bunches of your beam. Why is important? Is everything that you do here, you will find also in the other accelerators, because these are the same protons or ions that we'll find in the next one. We say that proton ions accelerator has memory, because you do something, you will find later the same. Any question? We have a wide range of people. We are not always in the same box. People think that we are always geek, nerd. Myself, I like to play football. I'm half Brazilian, so I must play football.
So Sven and Monica apparently get the impression that everybody working at CERN is Brazilian or half Brazilian. We have met so many Brazilians so far.
Okay, I'm half Italian, which doesn't change much because actually there is way more Italian than Brazilian here.
But you're the first Italian.
Oh. This one, the blue car.
Where are we going now?
To Trevisan, the other side of CERN. So it was not me. Yeah, but I'm always afraid that they could be under my car, and this car doesn't make any noise, and it's dangerous for the cats. Do you have your access, right? Yeah. Yeah. Actually, there is a tunnel that goes to that place, but that is only accessible if everyone has a CERN card. It's kind of the SM18 is the factory of the magnets, actually. Also, it's possible to visit, but I don't have access there. Sorry. So, for the LHC ones, which are superconductive, they are not conventional conductors. They use niobium. It's a special element to when you go to very low temperature, very close to the absolute zero Kelvin, they become superconductive, so they don't have impedance. So you are not wasting energy in generating the magnetic field. But still, we have 1/3 of the consumption of energy of the whole canton of Geneva. So canton is kind of, canton is not only the city of Geneva, but all the region of Geneva. We spend 1/3 of the energy. This is because we need, first of all, for LHC, the energy to refrigerate, so to have cryogenicity, to lower the temperature of the helium that cooled the niobium. But actually, this one is not the one that consumes more energy. The one that consumes more energy is actually SPS. It's smaller, 7 kilometer against the 27 kilometer of LHC, but is a conventional, has a normal conductor, normal magnets, and that consume way more energy, even if it's smaller.
How many people work on the accelerator?
Accelerator complex is smaller than an experiment. I would say scientists around 1,000, but you have all the technical people that you need for the operation, and there I think there are way more than experiments, the technical people. I was in experiments, and so I did several things. I did during my PhD. Okay, before my PhD, my master, I was working with the study of it's anomalous coupling, so it's something that is not really, it's not proven, but it's not even in the theory itself of the standard model, with the specific detectors of CMS called PPS. And then later I did X measurement with a specific channel, XWW, and was lucky that during my PhD we did the first observation of XWW, so my thesis was about that. Then I kind of changed the focus of my search. I became a machine learning expert, so I did my previous postdoc particle reconstruction using neural networks, deep learning, and now I use actually deep learning for the design of new accelerators. So there is still a link, but yeah, it's a very different field of physics. It's yeah. I don't know if you know that this new building here next will be the new data center. The new building that they're building, they're constructing.
It's the first time for me at CCC. I have never been here.
Oh, okay. Before going to this control room, I want to show you even more about accelerators. Some nice instruments that we have inside the accelerator now that I want to talk about it. So this is we call wire scanner. So there is laser. Oh no, there is no laser here. So basically what it does is this is standard, and when we want to make the measurement, this wire goes in and then goes out. It has a differential of potential, and so meaning that it will have a Colombian interaction with the beam. And as you can see here in this video, it will basically measuring where is the position of the beam depending on this interaction. Then you need two of them, because with only one dimension you don't know the shape of the bunch, but if you have two and you know that because of the quadrupoles actually the bunches they rotate, you can actually with two of them know what is the 2D shape.
Just to give them an idea about the dimensions of the beam.
Okay. They say that is. Let me see if they have a coin here. I don't. Yes, I have it. So they say that is the size of the Iberic Peninsula. So it's very, very tiny beam. And yeah. The beam pipe is T size, the beam is T's one, but you wanted to actually leave that region to not interact with the wall. When the beam interacts with the wall, you lose the particle. Okay, so now I wanted to show the control room. Not this one. Is this one? So this is the control room of CERN.
Holy crap.
Okay, I think if you want, I just have to ask the chief over there if we are allowed to get in.
Also ich nehme alles zurück, was ich gesagt habe. Mein Lieblingskontrollraum ist CCC, ist nicht der Atlas-Kontrollraum, auch nicht CMS. Das ist schon ziemlich cool.
Perfect, we can go inside.
That's great.
As I say, we have here 4 islands. This is the island for LHC. This is the island for SPS. That is the island for PS and the booster. And then this is the island for cryogenesis, so to cool down the magnets of the experiment, of the accelerator of LHC. What we can see here, okay, first of all, we have a lot of tanking from the experiment. This bottle actually comes from the experiment tanking the beam that were used for discoveries, for observations. What else we can see? So that is the main page of LHC, is the one that is written beam setup, ramp down, so the operator also can make a comment what is happening. Then later would be a field to actually do the measurement of the aperture, as I was saying before. Also from these computers we can control many aspects of the frequency of the current of the quadruples or the sextuple octuple, in order this will change the frequency, so the betatron frequency, we can change that. We can change the frequency, we can operate the machine, we can change the collimator's position I was mentioning, so from all these computers. I'll try to show you AMS, but I think it's not really possible to see anything. IMS is an experiment that is in the ISS, is the International Space Station. We have this detector, particle detector, to do measurement of basically cosmic rays. I don't work here, and I don't have access here, sorry. But I think it's interesting because it's pretty different from. We can study particle physics in 2 ways. In nature, so studying cosmic rays, or we need to build an accelerator to generate our particle to be studied. Okay, this door is allowed to open, it's possible to open, but this one not. Commenting what he was saying about LHC operation, first of all, when we are actually taking data, generally we do during the night, and also we stop during winter because of energy consumption. Because if you have to warm up the region plus having an accelerator working is a bit too demanding for energy, and then we stop and we take that time actually to do our manutention, updates, upgrades, and so on.
I'm completely blown away. Very nice. Thank you very much, Davide.
Bonsoir. And merci beaucoup, bonne soirée. We are going here, so I want to park somewhere close. So this is actually the first accelerator of CERN. In the past, they didn't have any building here. And yeah. Oh, someone is inside. Okay, we can go. So particle physics is the area that studies the element component of the universe, not the matter of the universe itself. For studying that, we study basically two groups of particles. A group is called fermions, which are all the particles that compose the matter. Electron, muon, quarks, the quarks that compose protons, neutrons. So fermions. And the other one are the bosons. Now I have to explain what is a boson. That is also important. It's not matter, it's not antimatter, matter and antimatter. It's of fermions. Bosons are the particles that are responsible to create interaction. I will make an example to illustrate all the other bosons. The simpler one is the electromagnetic interaction. So when you have two charges, same charge they will repel, with the opposite charge they will attract. But for a particle physics, what happens there is that there is a third particle that will mediate, means that it will exchange information between these two charges. In the case of the electromagnetic interaction, this boson is the photon. We have other interaction that could be they can be forces, like we have the gravity, the gravitational force, and also we have the strong and the weak force. By studying the fermions and bosons, so we can understand what the universe is made of and how they interact with each other. Why I need to talk about these is because also I want to talk one of the forces, the strong force. Because this experiment was responsible to the observation of a phenomenon that they were looking for such a long time, and it was observed here. So, Yukawa in the 30s suggested a new force, it's called strong, in order to explain why the nuclei of 8 atoms are stable. So we know that the atom is stable because we have a nuclei which is charged positively, an electron is negative charge, so there is an electron interaction, and so the electron doesn't go away, it stays stable inside the atom for years. But why the nuclei is stable? Because, okay, not hydrogen, but if you take helium, has already 2 protons, 2 neutrons, the neutrons should not interact, they can go anywhere, but the protons should actually repel and not stay stable inside the nuclei. So Yukawa had this idea of having another force which is stronger than the electromagnetic. So it's a genius. Huh? This is I'm not sure, it's in the 30s. I think 34, I'm not sure exactly the date. And the particle that, the mediator of this force between the nucleons was observed only in 47. So it was a visionary. And so it's genius, but not so creative, because it gives the name of the force strong force just because it's stronger than the electromagnetic. And then we have another force that is the weak one, and is called weak because it's weaker than the electromagnetic one. So why I'm talking about strong forces is because here we observe the first decayment of the pion to electrons. This pion was responsible to actually prove the idea behind Yukawa that there is a strong force and you need a mediator between the nucleons for this interaction. And the pion is this particle. So it was discovered in 47, studying cosmic rays. It was a Nobel Prize for Cecil Powell. There is a Brazilian in the group, actually. It's a famous because also it's a creative institute where Carsten work. It's Cesar Lattes, and the third researcher is an Italian one, Occhialini. Okay, 47 they discovered the pion, but this pion will decay to muons, and only in 57, so when they operate this machine after few hours, they actually observe the pion decay to electron. So this is kind of impressive. It was not possible just by studying cosmic rays. So this is also to illustrate why we need accelerator, because in nature we don't have control of the energy, neither of the frequency of the events. And to make an observation, so make a discovery, sometimes you need a rate, so you need statistics, and sometimes you need energy because you want to observe something that is heavy and yeah. This is a very different accelerator. I can explain in a few words what we have here. So we have a vacuum chamber inside because we always need vacuum, otherwise the particle will interact with the air and they will interact. You don't want to have any other interaction. We have a solenoid or magnet to provide a magnetic field in this direction in order to bend the particles. So it's always perpendicular. So if the magnet field is inside, they will bend in this direction. And then here we have two conductors in shape of these, electroconductors in shape of D. So imagine it's round, and then we have two Ds. When the particle will go, there is these Ds will have a polarity. One will be positive, the other will be negative. And they will accelerate one direction. Then, because of the magnetic field, the particle will bend and go to the other direction. You invert the polarity. There will be in between the gap, there is the electric field, similar to what we see before. So they will accelerate to one D to the other. They will curve and invert the polarity and again gain more energy. And from very small circle, they will start to do like an ellipsoid movement, because the magnetic field will be the same, but the velocity will get higher, so they will, until they are very close to the wall of the vacuum chamber, and then you eject and study what you want to see. You want to. Okay, so this is a very different, the name is Cyclotron, it's with C. The other is a synchrotron with S. And actually this is a bit specific, actually this is a synchrocyclotron, because actually the frequency can adapt. Okay, it's already night.
Thank you so much, David. That's amazing, amazing.
Happy that you enjoyed it. Where should you drop you off?
My car's at your
Okay,
office.
let's go.
Yep.